to be in the neighborhood of 12.47. Now look at the measured values. If you notice that heat capacity at constant pressure for helium, neon, argon, krypton, xenon, they all agree. There you are. And the heat capacity at constant volume also agree. And look at this, CMP minus CMV must be equal to approximately R, and this is a good agreement. But come to diatomic molecule, nitrogen, hydrogen, oxygen, there is a big difference between the measured experimental values and the theoretical values. The theoretical values suggest that all gases must have this as the heat capacity, molar heat capacity at constant pressure, and all gases must have this value as the molar heat capacity at constant volume. Well, experimental measurement shows that it is true for monoatomic gases, but not true for diatomic and polyatomic gases. Where have we gone wrong? Where have we gone wrong? Well, I can tell you where we have gone wrong. Now, you remember in obtaining the internal energy of a gas as 3/2 nKT, or the energy per molecule. If you remember, we started here. The energy per molecule is 3/2 kT. Now, we said the energy for X motion is 1/2 kT, the energy for Y motion is 1/2 kT, and the energy for the Z motion is 1/2 kT. I hope you remember the concept of degree of freedom that I introduced. You see, in the lesson on kinetic theory, what we obtained is that energy of a molecule per degree of freedom is 1/2 kT. And we said a molecule has 3 degrees of freedom. You see, it can move in the X direction, Y direction, and Z direction. And therefore, the total energy of a molecule is 3 times 1/2 kT, which is 3/2 kT. Well, this assumption is true for monoatomic gases. You see, our experimental measurements agrees well with the results for the monoatomic gases. That means a monoatomic gas. What's a monoatomic gas? Well, each molecule or each atom exists on its own. That means they are not coupled with any other atoms. So this is a single atom, and each single atom has 3 degrees of freedom. That's fine. But in the case of a diatomic gas, look at this, a hydrogen molecule exists like this. That means in addition to their X, Y, and Z motion, these molecules can actually rotate about 2 different axes. They can rotate. So that introduces another degree of freedom. Because they can rotate about 2 axes, it introduces 2 additional degrees of freedom. Now look at the way we go and revisit our theory and make corrections to our assumptions that we made earlier. So, what is the correction now we have to apply here? It is not a very small correction. We will explain this discrepancy using the equipartition theorem. What is it? In the lesson on kinetic theory of gases, you saw that the energy associated with motion of a molecule in the X direction is 1/2 kT. The ability of a molecule to move in the X, Y, and Z directions are called degrees of freedom. a molecule consisting of just one atom, called a monatomic molecule, has the freedom to move in the X, Y, or Z directions. In other words, a monatomic molecule has 3 degrees of freedom: X, Y, and Z. All right. The energy associated with each degree of freedom we obtained again in the class on kinetic theory as 1/2 kT. Therefore, the total energy of a monoatomic molecule is 3/2 kT. And that is what we based our theory on specific heat on. If a monoatomic gas consists of n moles, each mole containing Na molecules, the total number of molecules will be number of moles times the number of molecules per mole. We have seen that earlier. So the total internal energy U of n moles of this gas is U equal to 3/2 n Na kT. And do you remember, Na times K is what we call the universal gas constant, equal to 3/2 nRT. And this is what we concluded earlier on, which apparently is quite right for this kind of gases. Now, this is consistent with experimental results. All right. A diatomic molecule, on the other hand, is made up of 2 atoms, and the combination, in addition to their X, Y, and Z motion, can rotate about 2 axes other than the axis containing the line joining the 2 atoms. Now, here is a diatomic molecule. Now, this molecule, in addition to the X, Y, and Z motion, that molecule can vibrate, can rotate. Now, it cannot rotate, if this is the diatomic molecule, it cannot rotate about this axis, but it can rotate about an axis of right angles. Look at that. It can rotate like this, it can rotate like this. So, a diatomic molecules, now you got assigned 2 additional degree of freedom. Now, this adds 2 additional degree of freedom to a diatomic molecule, bringing the total number of degrees of freedom to 5. So, the number of degrees of freedom of a diatomic molecule is now 5. Now, what is the energy associated with each degree of freedom? Is 1/2 kT. Therefore, what is the total energy of a diatomic molecule? It will be 5 times 1/2 kT. Since the energy of a molecule per degree of freedom is 1/2 kT, the total energy of a diatomic molecule is 5/2 kT. Now, the internal energy of n moles of such a diatomic molecules will be, the total internal energy is 5/2 nRT. You see, look at the correction we are now applying. Now, earlier we said the internal energy of all gases is 3/2 nRT, because we assigned only 3 degrees of freedom to every gas. But now you know diatomic molecules have 5 degrees of freedom. Therefore, the internal energy of n moles of a gas is 5/2 nRT. And that will now change our heat capacity values. So, internal energy is 5/2 nRT. Therefore, for a diatomic gas, now tell me, what is du/dt equal to? Du/dt equal to if you find the derivative of u with respect to t, we get du over dt equal to 5 over 2 nr. And, well, this is per mole. Well, if you divide this quantity by n, now let me show that to you. Now here, our C, the energy per mole U over N equal to 5 over 2 RT. And now, this is the internal energy per mole. If you now take the derivative of this quantity with respect to T, that will be CMV. So CMV equal to 5 over 2R. What was the value we had got earlier? Earlier we got 3 over 2R. But that is true for monoatomic gas. So you must distinguish. For a monoatomic gas, CMV is 3 over 2R. But for a diatomic gas, CMV is 5 over 2R. Okay. And that will be 20.788 joules per mole per Kelvin. And if you now look at the values for diatomic gas, CMV must be 5 over 2R. Now, do they agree? Yes, they agree absolutely. And how about CMP? CMP then will be 7 over 2R. And that must be equal to 29.103. So we didn't have to do a lot of big corrections. As soon as you figure out what we omitted, well, we are back in business again. So our theory is actually very, very good. These values agree fairly well with the measured values, and therefore our theoretical considerations are based on solid grounds now. Now, polyatomic gases. Now, this is beyond this class. They are much more complex. The degrees of freedom of polyatomic gases are much more complex. So we will ignore that. We will not consider. We will only take monoatomic gases and diatomic gases and leave polyatomic gases for anybody who wants to do higher classes in physics.